Hey everyone, last time we introduced the idea of simple group, right? Remember, a non-trivial group is simple if the only normal subgroups it has are the trivial subgroup and the whole group itself. And then we talked about how the fact that the alternating groups are simple for n greater than or equal to 5 leads to this theorem of Galois theory that says that polynomials of degree 5 or greater do not have a general formula for factorization, right? They're the so-called not solvable by radicals. If you go on to Math 483, we'll actually talk about that in detail. So that would be in the spring. Simple groups, that's not the only place that simple groups are important. And so I want to continue the study of normal groups and simple groups. And so this next theorem right here, I think I just said normal groups, I meant normal subgroups. So theorem 15.8, this is going to tell us how normal subgroups behave under homomorphisms. So let's let phi from G to G prime be a homomorphism. Two parts. So the first part, if we start off with a normal subgroup of the domain, so if n is a normal subgroup of G, right, then phi of n, so the image of n, is a normal subgroup of the image of phi. And then part B, if let's call it n prime is a normal subgroup of the image of G, then the inverse image of n prime is a normal subgroup of G. So normal subgroups get taken to normal subgroups of the image of the function. You have to be a little bit careful here. Now in part B, it actually turns out I could replace this this phi of G with all of G prime if you want, but since we're looking at inverse images, it makes sense to only look at the image of the function in the first place. So you can interpret this as inverse images of normal subgroups are normal. So for the proof, I'm going to prove part A, and then we'll leave part B as an exercise. So for part A, okay, so I want to show that phi of n is a normal subgroup of phi of G. And the way I'm going to do that, I'm going to apply the normal subgroup test. So, how do I want to do this? Let's let G, do I want to call it G? No, let's call it X. Let X be an element of phi of G. So what I want to do is I want to look at the conjugate x times phi of n times x inverse. I need to show that that is contained inside phi of n. All right, I'm applying the normal subgroup test. So let's see, what does it mean to live in phi of G? So then x is equal to phi of little g for some little g in capital G. Okay, so now what I want to do, let's pick somebody in the conjugate of phi of n. So that would be, let's pick, how about y in x phi of n times x inverse. Okay, so then y is equal to, well, okay, let's write it like this. X, what symbol have I not used yet? How about z? X, z, x inverse for some z in phi of n. Okay, so what does z look like? So so now we have z is equal to phi of little n for some little n in capital N. And so now let's see what y looks like. So y equals. Okay, x can be expressed as phi of g. So this will be phi of g. Then z is phi of n, and x inverse is phi of g inverse. I can combine all that, so this would be equal to phi of gn g inverse, right? Phi is a homomorphism, so I can put everything in one piece. Okay, now where does gn g inverse live? Well, because n is normal, we know that gn g inverse lives inside n. So since n is a normal subgroup of G, we have Gn G inverse is in n. And so what does that mean then? That means that phi of Gn G inverse is an element of phi of G. So let me we have this. Let's finish this off. And so phi of G n G inverse, which is y. And so let me make this sentence look a little better. And so y, which equals phi of G n G inverse, is an element of phi of n. So what did we do? We started off with y in x phi of n x inverse, and we ended up in phi of n. So we can say therefore x phi of n x inverse is contained in phi of n. And now we can just quote the normal subgroup test. So by the normal subgroup test, phi of n is a normal subgroup of phi of g. Notice it was key that right here we wrote phi of g rather than g prime, because at a certain point in the proof, right, I had phi of g, right? I was able to use phi of g. That was because the element that we are conjugating by lived in capital, or phi of capital G. Right, so hopefully you can see where we use that fact in the proof. I'll let B, part B, that's a good one for you to try. So B is an exercise. And so we're done with that proof. Now for a definition. A proper subgroup, I want to call it M of G, is a maximal normal subgroup of G if, okay, so somehow we want it to be the biggest of possible normal subgroups. And so it would go like this. Well, I should say it's normal also, right? A proper subgroup if, so if M is normal, obviously, if we're going to call it a maximal normal subgroup, it better be normal. And there is no normal subgroup, so subgroup N normal in G such that, oh, and I gotta say proper here, don't I? There is no proper normal subgroup say, n in G such that, normal subgroup that properly, let's say it this way, that properly contains M. So it's kind of a tongue twister of a definition, not my favorite definition in the world, but the idea, M is going to be a maximal normal subgroup if number one, it's normal, and number two, there's no bigger normal subgroup that contains it. And here proper, there's no bigger proper normal subgroup. So obviously G contains it and G is normal, but we don't count that. Right? So it's the biggest of the proper normal subgroups sitting inside G. So for example, 3Z is a maximal normal subgroup of Z, but 4Z is not. And the reason, right, what we have is, right, yes, 4Z is a normal subgroup of Z, but it's contained, properly contained, in 2Z, which is a proper normal subgroup of Z. So here, notice what I'm writing here. 4Z is properly contained in 2Z, so it's contained but not equal. 2Z is a normal subgroup that is not equal to all of Z, right? So this is the situation where here's our M, here's our N, this is the bad thing right there, right? We have a bigger normal subgroup containing our normal subgroup. Okay, so there's a definition, and it turns out that there's a connection between maximal normal subgroups and simple groups. So theorem, this is only 15.9. So M is a maximal normal subgroup of G, I guess, yeah, G, if and only if G mod M is simple. All right, so there's an interesting fact. I mean, somehow what it's saying is that to get a quotient that is a simple group, you need to quotient out by a normal subgroup that is as big as possible. Right? And by doing so, what you do is in the quotient, you kill off the possibility of any non-trivial proper normal subgroups. Okay, so for the proof, okay, so let's assume we're going in the forward direction first. So let's assume M is a maximal normal subgroup. And now our job is to show that there are no normal subgroups let's say no non-trivial proper normal subgroups of G mod N. And so I want a little piece of technology here. So normal subgroup, let's say, and let eta from G to G mod M be the natural projection, right? So what it does, it takes each element to its corresponding coset. Now, suppose that, so let's call it, what do I want to call it? N? Yeah. So suppose N is a normal subgroup of G mod M, which, by the way, G mod M is equal to the image of G. So suppose this, right, is a normal subgroup, and we want this to be non-trivial. So suppose this is non-trivial. Now, remember what we're trying to do. We want to show that this quotient G mod M is simple. Simple groups can have no non-trivial proper normal subgroups. So if I've stated here that we've got a normal subgroup that's non-trivial, right, to conclude that G mod M is simple, what we would need to show is that N is all of G mod M. So by our previous theorem, so that was 15.8, the inverse image of N is a normal subgroup of G. Now, okay, so the next one, so since the trivial subgroup in G mod M is contained in, but not equal to, N. We have, so I need to be a little bit careful here, so we have that M is contained but not equal to the image, the inverse image of N. Okay, so now what do we know about this? This tells us then, so let's see, M is a maximal normal subgroup. So the only way that we can have this situation where M is properly contained inside this normal subgroup right here, the only way for that to happen is for this to be all of G. So it follows that the inverse image of N is equal to G, and so N, which is equal to how do I want to say that, N, apply eta to both sides of this, N is equal to eta of G, and eta of G is everything, right, G mod M. Right, so that's what we needed. Sorry, I got a little tongue-tied there, but the idea is we chose a non-trivial normal subgroup, and by doing a little bit of work, it forced us to conclude that N is equal to the entire group G mod M. Okay? In other words, there are no non-trivial proper normal subgroups of G mod M. Okay, so now in the reverse direction, okay, so let's assume G mod M is simple, and now our job is to, let's see, what do we need to do? We need to show that M is not properly contained in any proper normal subgroup of G. So, so let's say, suppose, let's say, and suppose that M is contained, properly contained in, what symbol am I using? Where'd it go? Oh, in the normal subgroup N of G. So our job then is to prove that n is equal to g, right? That'll do the job. That'll force us to, or that will allow us to conclude that M is a maximal normal subgroup. So then, if I apply eta, I have eta of n is a non-trivial normal subgroup of the image of phi of eta, eta of g, which is equal to g mod m. This is by, and I should point out, so this is by theorem 15.8. Now, now what do we know? We know that g mod m is simple. So since g mod m is simple, it follows that, okay, so what do we have? We have a non-trivial normal subgroup of g mod m. That forces us to conclude, right, that it's actually equal to all of g mod n. So it follows that eta of n is equal to g mod m. And now my claim is that n now has to equal g. Right? That's what we need to conclude that M is a maximal normal subgroup. I can't have this situation unless n is actually equal to g. So there's the claim. N is equal to g, and so we need to prove this claim. And so, of course, n is a subset of g. I want to show that g is a subset of n. So let's pick little g and capital G. And then eta of little g is equal to g times m. And this is an element of eta of what? Oh, it's an element of eta of n. And so, well, let's see, what does eta of n look like? It looks like all cosets of the form little n times capital M. And so what that means is that gm is equal to n times m for some n in, some n in capital N. Now, since, what do we have? We have, since m is contained in capital N, we have gm, that's equal to nm, which is contained in n, which is equal to capital N. Therefore, is that how I want to write it? Yeah, therefore, little g is an element of capital N, and that's what we needed. Right? We have g times something in n lives in n. That means that g has to live inside n also. Okay, so that completes the proof, or well, I guess that's the end of the claim. Right, so claim done. And what does that tell us? It tells us that G, that tells us that N is equal to G, and that's what we needed. So let me write a little concluding sentence here. We have shown that that the only proper or the only normal subgroup of G that properly contains M is G. All right. Therefore, M is maximal. I'll say thus M is maximal, and that completes the proof. Okay, so that's a good place to stop. We will see you next time. We'll continue our study of normal groups, or normal subgroups, simple groups, and so on.